All right. My name is Austin Rose, and I'm here with my partner, Michele Orlandi. And for the Kaggle Hackathon, we wanted to analyze how the tools we use has evolved over time, either leading us to or as a result of developments in the machine learning or artificial intelligence fields. Using the provided source code data and associated metadata, we examine the change in usage of different libraries, modules, and functions as they relate to the most popular competition types on Kaggle. So after importing some libraries here and defining our working and metacode directories, as well as some helpful plotting functions that we will use later on, we can get into our code here. So in order to properly utilize the data stored inside of the nearly 300 gigabytes of code files, it was necessary to parse these files and extract useful features from the data. The primary functions we use to do this are parse pyline, add key, and analyze py files, which are found down here. So in parse pyline, which does the bulk of the work for the analysis, essentially we walk through each line of the file, excluding or trimming lines with comments, as identified with an octothorpe or a hashtag for the younger generation. From there, each lining with from or as was tagged as an import line, and the library that it imported as well as its alias was mapped to the libdict that we initialize in the beginning of the function. So if you import pandas as PD, then we search for the alias PD throughout the rest of the file and then later map it back to the pandas library. Then we look for a number of cases here. Essentially, these are libraries that have a dot after them or an open parentheses after them. And we look for three different cases around that, lines that start with a space, lines that start with an open parentheses or the substring contains starts with an open parentheses, and a line that just starts with this call in the beginning. In order to keep track of all this, we have this add key function up here where we pass in a period or dot delimited key, and that is the full path. So it would be pandas dot data frame or something like that. We then recurse through the dictionary and increment the count of each key by one for the keys that we have already. Um, then we have this parse py files function, which goes through a list of a whole file and does this output all for one. And it goes through for py files as well as notebook files. Now that we had a way to analyze each of these code files and extract some useful information from it, we decided it was time to generate a list of kernels to analyze. And we put that back up here. So first we looked at the kernels tables and saw that the only way to get that kernel version, which is the way that we needed to map it to the code files, was to use either the current kernel version or the parent kernel version. Now we took the current one where the parent one was we took the parent one where the current one was not available. We also looked at the competitions table and the competitions tags table to get the competition ID and the relative tags related to that competition. Now, using that in the previous result, we could connect a kernel version to zero or more tags, depending on whether that kernel was tied to a competition and whether the competition was tied to any tags. And we took that tag and we split it into two parts. We took the first part of the tag and we called that the tag domain. And we took the second part of the tag and we called that the tag source or the tag name. And so you can see a sample of our data down here. We've got the tag domains here, and we got data type, technique. And then we have the specific tag name, which is a little bit more granular. And we can tie that all the way to competitions with different reward types and kernel IDs. So the last step in our pre-processing process here was to look at which were the most popular kernel domains that we wanted to look at. We decided we wanted to look at 10. So in order to decide which the most popular were, we defined a popularity score here as 0.5 times the total votes on a kernel, 0.45 times the total views, and 0.05 times the total number of comments, and we summed those three variables and we gave that as the popularity score. We then took the mean of the popularity score for each of our tag domain combinations over the years, and we aggregated that and we took the top 10, and those can be shown below. Now that we had that complete, it would be time to begin post-analysis.
Now that we've identified the most popular domain name combinations, let us dig a little bit further deeper in them. Firstly, we examine the distribution of popularity scores for each of the domain name competitions. As shown in the sample plot here, the interesting observation is that all these domains name combinations and their distributions are heavily skewed to the right, showing how very few competitors contribute to the popularity of a particular domain. Now, our question is, how do these kernels achieve such recognitions? Our hypothesis is that the answer may lie in the types of packages and modules used. The clean metrics function allows us to retrieve and combine at the domain name gear level the usage frequency of each module and submodule. Its output is a consolidated data frame where each row indicates the number of distinct kernels in which a module was used in a particular year for a specific domain name combination, along with the total number of kernels for this combination. Thanks to this data frame, we can calculate the utilization rate simply as the count over total kernels and the year-over-year change in package utilization under each domain name. To focus on the most impactful and popular packages, we filter out those whose mean utilization change is less than the 25th percentile of the entire population. The charts below highlight these utilization trends over time for some of the most popular domain name combinations. It is interesting to note how these charts tend to highlight packages that are critical in many ways to the foundational techniques within these domains. For example, in signal processing, we see a great increase in exponential weighted moving averages or Hahn smoothing functions, typically used for removing noise in signal processing. Or in the data type video, we see a slight increase in the latest year in the use of BlazeFace, Google sponsored package for face recognitions in videos. Finally, we were interested in understanding the impact that the usage of these packages may have on the popularity of a particular domain. To achieve this, we combined the package utilization change across the most popular domains in years, together with the yearly mean reward quantity for those competitions, as well as the yearly average number of competitors. This dataset, minus any visualization or other simple packages like OS and sys, constitutes our independent variable matrix, while the yearly average popularity, excuse me, is our response. Due to the high dimensionality of this dataset, we had to perform some regularization to perform any regression analysis. Therefore, we chose to perform a lasso regression, where the L1 penalty that is applied to the coefficients during the loss function minimization may shrink some of the coefficients to zero, effectively performing an automated feature selection. The results are shown in the cell below. We notice that out of the selected coefficients, those packages that imply a higher level of code complexity and nuance tend to have a greater positive effect on the average popularity of a domain, while simpler ones tend to have the opposite effect. This highlights perhaps the high code quality standards that the Kaggle community rewards and is interested in. In conclusion, despite the old data science motto that complexity is not always better, our analysis shows how leveraging more complex and nuanced tools may actually lead to a better performance in competitions and a popularity of one's kernel. Unsurprisingly, I might add, given the role of Kaggle at the forefront of innovation in ML and AI research and development. Future work on this topic may address further nuances of this data, perhaps at a more granular level, like a month-over-month analysis, and covering a broader spectrum of categories, competitions, and kernels. Additionally, further development may be done in our parse pi function, where we could be able to extract more detailed and complex information from the script themselves. We want to thank you very much for this opportunity, your time, and your feedback throughout this competition. Thank you very much.